All right, everybody. It's a special pleasure to host Zoha today. Zoha is a former student of mine, and she's currently doing a PhD at the University of Tennessee, Knoxville. She's going to be talking about many body simulations of neutrino oscillations. Zoha, over to you.
All right, thank you so much for having me here. It is a pleasure to be talking about my work. Yeah. So this one is in collaboration with, of course, my University of Tennessee, and then some work that I've been doing as part of my internships at Oak Ridge National Lab and Los Alamos National Lab in the US. So I'm currently finishing my PhD right now, hopefully within the next few months. So this is part of the research that I have conducted over the years, my PhD. So without any further delays, I will start with first introducing what neutrinos are. Oh, did I say the anyway? So I'm going to be talking about many body simulations of neutrino oscillations in supernovae. So I'm going to first introduce what neutrinos are and why they are important in supernovae, and then how do we model their many body approach on such systems. Then I subdivided into section A's and section B's, where I talk about what happens if I do homogeneous simulations of these neutrinos on classical computers, and then how do we do it on quantum computers. And I do the same for inhomogeneous conditions for classical and quantum computers. And then I just briefly summarize what we have some takeaways from the talk. So neutrinos, they are fundamental particles belonging from the lepton group. They do not participate in strong interactions. They just weakly interact. And then they're created from radioactive decays and nuclear reactions and those sort of things. They're very difficult to detect. They do not undergo electromagnetic interactions. But the most important part is that in this sun model picture of neutrinos, they do not oscillate between different flavors. So we know from our experiments that neutrinos come in mass eigenstates and also their flavor eigenstates. So they can oscillate between different masses and vice versa as their flavor eigenstate by their unitary operator U, given in two flavors as cosine and sines of this mixing angle theta. So for the rest of my talk, I will not be considering neutrinos as three elements, like three flavors. I will be approximating into two flavors, saying that one of the flavors is electron and the other is just the heavy flavors for simplicity, so that I have an SU2 group to deal with and not SU3. So the very important thing that they do and the harder thing that they do is they flavor oscillate between different bases. That's very rare that other particles do not really do such a thing. And so the trivial ones are coming from when they propagate in vacuum. And then since they are in their mass eigenstate and like they have different masses, they are driven by this angular velocity, angular frequency coming from their mass differences of both the bases. So they can propagate in vacuum via vacuum oscillations. These are the trivial ones. Now, neutrinos can also interact with matter or the media they are in, and they can also produce some sort of oscillations and convert flavor in such a scenario. But the most non-trivial or the non-linear dynamics come from when these neutrinos interact with other neutrinos, and they scatter off in this background of neutrinos. And when these vacuum and neutrino-neutrino interaction, they are comparable to each other, they give us this collective flavor conversion, which are very important in supernovae. So let's talk about what really are the supernovae. So when we have a massive star, about 8 to the 8 solar masses, they end their life after the gravity is unable to, or it has exhausted its nuclear fuel, and so the gravity overcomes the electron degeneracy pressure. It overcomes gravity around hundreds of milliseconds. And so this is one of the simulations that we have from this very famous Flash X code in 3D, where right now I'm just going to start with 100 milliseconds. It's like a movie that's going to play. And so right now the core of the star has collapsed after all the onion layers it has built up, and now like under the gravity, it has collapsed. And now we evolve such that this collapsing core now undergoes neutronization which means more neutrons are being produced. And so when it hits the nuclear density, it's going to bounce up until, say, 300 milliseconds or so, and it's going to launch a shock wave. So right now we see, so this is so let me pause. So previously it was a proton-neutron star. It's going to start the collapse. And here we see slices off in the X, Y, and Z direction. That's what this shows. And this is just the supernova that we're talking about. And this is one of the simulations that we have at our group in University of Tennessee. So the idea is that as it builds up energy, it's going to produce a shock. And the shock wave will have some infalling stellar material inside. But around 300 or so, this shock will lose some energy. As we're going to see, the entropy is rising from below. So there's like this shock that comes in between. But neutrinos have a very big part to play because this shock eventually stalls for a little bit, and then this neutrino helps to make this explosion go throughout all the way. So these neutrinos are important because most of the gravitational binding energy is released in form of these neutrinos, about 10 to the 53 ergs, which is a lot in energy, and about 10 to the 58 neutrinos are emitted in about 10 seconds. So those are a lot many neutrinos to be dealing with. They are responsible for or could revive the stalled shock and are released in all neutrino species, so electron, muon, and tauon in tens of MeVs. And the most important thing, among the most important thing they do is they impact the nucleosynthesis by contributing to the neutronization or by the electron fraction through neutron to proton ratio, such that the proton-neutron star that was left over has some more neutrons, for example, and contributes to a different neutron star after it has cooled in the supernova. So really, this is the shape that we're dealing with. We have a proton-neutron star. It is emitting neutrinos. It has some matter also accreting back onto the proton-neutron star, and we have to deal with this neutron to proton ratio that will govern the nucleosynthesis. So now here we know that we have a lot of neutrinos being emitted because it's a neutrino dense environment. So like we said, there are vacuum oscillations, which are one-body terms, and those are trivial to deal with that are coming out of this proton-neutron star. And so if we come up with this boundary, we have like these large densities, which will necessitate some self-interactions or the neutrino interactions that we talk about. So these would happen on fast timescales near the proton-neutron star and some at slow timescales a little further out of the proton-neutron star. So we can think of another neutrino beam with a momentum k, for example. It comes out, it interacts with neutrino with momentum L, swaps flavor. That was given by the cloud that I just showed. It goes out, it also swaps flavor again, interacting with another momentum J of a neutrino beam. And so the idea is, even though my mu L and mu J never really interacted with each other, they could still have some entanglement built up between these beams because their flavors could be related with each other. So there's some correlation that could develop between these beams because neutrinos interacted with each other. And so here we're dealing with collective oscillations or the collective effects, where our vacuum oscillations and our self-interactions are comparable with each other, where we're taking into account into forward scattering. So vacuum, like I said, was one body term where we have to deal with just one neutrino at a time, and things are easy. With self-interactions, I have to deal with a pairwise interaction. So I need to have at least two neutrinos that have to interact with each other. And then we have to also account for the relative angles between these neutrino beams given by these PIs and PJs. So Jij will govern the anisotropy in the system, and this mu will govern the interaction strength of the neutrino beams that are interacting. So N's are the neutrino densities of I and J beams, for example. So really, it's
effectively this is a spin chain?
Yeah, but now it has all-to-all interactions. So a spin chain will have just the nearest neighbor interaction. Yeah. So I interact all the pairs with each other. And so there are lots of neutrino beams coming out of the proton-neutron star. And so I have to deal with everything all at once.
Yeah. Long-range interaction in a spin chain with the transverse field.
Yeah.
Okay.
So it's really a many-body problem to be solved to solve for, or entanglement that could build up, especially in fast timescales, which could really impact the nucleosynthesis that I was talking about earlier, because they're near the proton-neutron star. So how am I doing on the time, actually? I think I'm going pretty slow.
You would know.
Okay. So the current state of the field does it in mean field approximation, where we just assume that these neutrino states are not entangled with each other. And so when that's the case, things are easy because I can do more. Yeah, I can do more. I can do more neutrino. I can solve for more neutrinos in my simulation. So our usual equation of state, or what we call a quantum kinetic equation, looks like such, where the left-hand side deals with all the neutrino transport that has to happen. This is just a 1D advection that would happen when things are informing in the matter. Here governs all the flavor transformation that has to happen, because I will be dealing with the entire Hamiltonian and the density matrix. And then I account for all the non-forward scattering terms in the left-hand side. Sorry, the rightmost side. And so we are able to come up with the quantum kinetic theory and mean field approximation, where so technically it's a 7D problem, but we could do linear stability analysis, where we can think of it as a 2D problem, such that we can map this density matrix and look at their off diagonals and see the solutions of those off diagonal terms when they are linearized. Equation of motion. That's another relative of mine. You can just join in. And so the idea is that the solutions so here I'm dealing with just a 2 neutrino problem, where one neutrino is an electron flavor and the other is an anti-electron flavor. So with this linear stability analysis, I don't have to do a 7D problem. I can just consider it, I can just linearize those equation of motion, look at the solutions. And if that omega comes out to be positive, I can have all those normal modes, and that could correspond to collective oscillations. But if my omega here is, if it's positive, I could have flavor instabilities, because it's going to be an exponential rise in my exponential growth in my solution. So that's what's really shown here. So I plot the off diagonals, and then I see for that exponential growth. And if there's an exponential growth, that would account for the flavor instabilities. That means that I have my flavor that's changing so rapidly, or it's transforming flavor so rapidly that it could impact the nucleosynthesis a lot faster than we anticipate. And so that's a very known mean field effect in the field. But for the many body, where we do not assume anymore that these neutrinos are entangled, we do not assume that they're not entangled. So we assume that they're entangled. With that, we have a lot of, say, complications, because that way we constrict our quantum kinetic equation into not even considering advection and not even looking at the non-forward scattering terms as of now. And even then, we're not very sure of what the quantum kinetic theory looks like, because one, it's tricky because my Hilbert space now scales as 2 to the n of the neutrinos that I'm dealing with, that are a lot for a many body simulation. And second, it's incomplete because I'm missing on a few terms, like I mentioned. So that's what we need to look for in the field. So the big question is, should I do a mean field or a many body simulation for this really huge problem of 10 to the 58 neutrinos that have? Early work said that if I compare my mean field and many body, the purple and the green lines, and I go higher in the number of neutrinos, my mean field and many body are automatically, like from the beginning, they're diverging. And so if I go into the thermodynamic limit of 10 to the 23 even, this is going to be a problem if I'm dealing with something that is many body in nature, and I'm just doing approximation of it right from the get-go. And then the field also says that if I do a long time evolution of these mean field and many body simulations, so I'm really comparing the green, the yellow, and the cyan lines, and if I plot their polarization vectors in x, y, z, the cyan and the yellow, they are a lot different in all 3 polarization component even for longer times. So these are 2 big problems at hand. And so we need to really come up with a framework for the kinetic theory that addresses these neutrino instabilities that are talked about, but it does it in an entangled environment and also in an inhomogeneous environment, because supernovas are inhomogeneous. Currently, people do it in homogeneous environments for many body simulations because that is easy and computationally less expensive. But we're not really dealing with realistic conditions there if we do such approximations. So when we talk about neutrinos as quantum states, for example, if we have an initial state which looks like a product state, we just have separable electrons and muons, or the higher or the high flavor state that I talked about. And if that's the case, it's a pure mean field situation where my polarization vector has a mod of 1. It's a spin on the Bloch sphere, and it's pointing up or down either way, but like it's a product state, so it's all mean field. But now if I build in some entanglement in the system, I cannot separate my electrons from my muons anymore. So that way my polarization vector, the length of it decreases from 1, so it goes beneath the Bloch sphere. So that's the first thing to look at when we're dealing with the mean field versus a many-body simulation, just calculate the length of it on the Bloch sphere. Just for a reminder, I'm going to be dealing with the two-flavor isospin network, which means all my spins in the up directions are electrons, and all my spins in the down directions are muons on the Bloch sphere. And so when my polarization vectors are good to go in my XYZ directions, I can just map out the density matrix components and have the entire information of the quantum state of the system. So things are solvable in that sense. And I can also compute the entanglement entropy of one body, saying that, for example, if my one neutrino is entangled with the rest of the ensemble of neutrinos, how I can look at that. So really, the question at hand is like, it's a many-body coupled system, which has to do the n amplitudes. And on top of that, we're now adding some complex geometry because I want these to be moving and interacting, but not everybody at once. And so that's all I have to deal with. So I will model it both on classical hardware and on quantum hardware. Both have its pros and cons. Quantum side is not that developed yet. Classical is developed, but there's like so many we can go up to in the number of things we talk about. So first, I'm going to talk about the homogeneous system, not talking about the inhomogeneous, where we account for the fact that they could be spatially different in their places. So let's model it on classical hardware. The ones that are done for exact methods are Bethencourt's methods, but we could do approximate methods like variational principal methods or tensor networks. What I basically do is just the tensor networks where we just go off from scalar in one dimension and just keep adding dimensions and just build up a tensor like that. And we do some SVD where, for example, if I had this 6-rank tensor, I will decompose it into different matrices, and then I can just cut off at some threshold value of my matrices such that I can approximate this into smaller matrices as an approximated way of the bigger tensor at hand. So for my classical methods, I'm going to be using tensor networks, and that's given in the tensor network iTensor's Julian library. And the motivation is to verify the folklore that says that mean field could be more dominant for larger n. It is very much talked about in the field, but there's very less studies that can actually support or discard this.
So why do people believe so?
Because some of the mathematical frameworks that they have built, that's not right now in my talk. So they say that it scales with the number of particles. So they say if it's scaling, so they say that mean field scales with n square, and then many body scales with n. So if we're already going to the 10 to the 58 limit, n squared and n is not any different. So that's what they say. But those are mostly mathematical statements. But we know that the exact methods can go up to some dozens of neutrinos. It's going by itself. And so if I need to go in higher number of neutrinos, I use tensor networks. And the idea is to explore scaling and see if I can use a smaller bond dimension or a larger cutoff. I will explain those terms right now. And I need to see if I can just get away with doing more neutrinos with such conditions. So it's a quantum state, so we're dealing with a many-body Schrodinger equation solution, where, for example, if I had the 6-rank tensor, or that's how the quantum state is supposed to look like. What we do in tensor networks is that we use this MPS representation, matrix product state, where we take this n-rank tensor and we decompose it into smaller 2-rank, 3-rank tensors. So diagrammatically, it looks like that. So instead of dealing with this really huge tensor, I try to dial the entanglement between this A1 here, like I mentioned, and then I have these n6-legged sites separated out like that in this SVD. So this is an approximated way of looking at the full tensor like that. I evolved the state, and then I used tautorization, and then I also allow my neutrinos to be changing positions with different times. And then I dial the entanglement between adjacent sites via a bond dimension or a cutoff. And so that cutoff was really the value of the truncation that I do in my SVD shown on the last slide. So that way I can dial more entanglement or less entanglement between the sites. The good thing it does is that it scales my Hilbert space that first scaled with the exponentially in the number of neutrinos to now that it scales in linearly in the number of neutrinos, but square to the bond dimension, really. So the idea is if I have a bond dimension of 1, I have all my mean field, I extract all my mean field dynamics from there, and I have no entanglement in my system. But if I have bond dimension greater than 1, the dimension between the sites, I extract the many-body, and then I can go up to an infinite limit of bond dimension to really extract all the many-body behavior that is supposed to exist between adjacent sites. And that way I can sustain my entanglement in the system.
A bond dimension one mean that connected to only one.
Yes, so
nearest neighbor.
Right, so bond dimension 1 really truncates all the values in my matrix and just keeps one value. And that one value is supposed to be the biggest value that is to account for the mean field dynamics. That's what it does. And so that way I have all my sites connected is the product state I was mentioning, which was again a mean field when it's just truncated to one value. So I can do that, or I can also use the cutoff of C is equals to 1 for mean field and C is equals to 0 for many body. So tensor networks is good in the sense that I can very easily transition from a mean field picture to a many body system by dialing these variables in my system. So really that's how it looks like. If I have 8 sites, I add on these gates corresponding to the one body operator or the two body operator, unitary gates, and then they just compact out and then leave me with one value for an observable when that's put on. And so when we map it out on classical hardware using I-tensors, like I mentioned, for just 2 particles, we see that if I plot the Z component and X and Y component, so X and Y was supposed to give me that exponential growth in the mean field dynamics. That's what we get. So that's good. We can reproduce the fast flavor instability, which said that, you know, if I have an exponential growth, it means my neutrinos are transforming flavor within each other very rapidly. That happens in a mean field. But since my code was able to do the same thing for a many body framework as well, I just dialed up that entanglement variable I talked about. And then we see no exponential growth at all, which means that under many body framework, I do not have these fast flavor instability. So when that shock happens, my neutrinos are not changing flavor as rapidly as I thought it was on those timescales that I talked about. So that's the main takeaway from here. Similarly, for the PZs, we have some oscillations in the many body, which are the flash lines, and the mean field just shows that instability that it dips down a little bit, and then it oscillates for the rest of its cycle. But really, that's that. We first reproduced the mean field results with a growth rate of 1124, which is a good growth rate that we have. And it also suggested that we could have some FFI being erased in the many body framework, even for like 2 particles. So we could do this again, the homogeneous system on quantum hardware. And for that, we just evolved the quantum circuit that's equivalent to the Hamiltonian I talked about. For the quantum hardware method, the first ingredient we talk about is how we encode the map. So since it was a 2-flavor approximation, my neutrino state is going to be an electron and a muon. With electrons as the 0 state because they are up in the direction on the block. So what happened to this diagram? It was supposed to be labeled. I don't know what happened there. But electrons are all up in Z direction and muons are all down in Z direction. So it corresponds to a 0 and a 1 computational base. And if I have any neutrinos, I could encode it into n qubits. And so my full quantum state looks like in computational basis of 0s and 1s as what it does on Bloch sphere with theta and phi angles. And so when we have the Hamiltonian, I could generate the quantum circuit with the vacuum oscillation and the self-interaction potential as a full unitary operator with an exponential expression like that. But that's expensive to do. So what we do is that we decompose these Hamiltonian components into the single body term and the 2-body term that I talked about. And so single body is easy. We just put one gate on one qubit and we're good to keep going. but that way I'm not really putting entanglement in the circuit. So I really need to have a 2-qubit gate so that I can entangle 2 qubits. And that comes from having this pairwise interaction because it entangles the I and J sites of all the Pauli matrices X, Y, and Z. So that's that. And in terms of a quantum circuit, it looks like that. We then trauterize it. I do it in the second order trauterization, which is just an approximated way of dealing with the exact unitary operator. And then I measure the qubit remaining in the 0 and 1 computational basis so that I have an idea of how much counts there are in sigma z and sigma z plus 1 and minus 1. We rotate the bases and do the same thing for x and y direction for sigma matrices. And we have our counts from there. So we can measure observables like that. So we have a preliminary result from from this internship that I did at Oak Ridge, where we use the same MPS simulator and we try to reproduce the mean field approximation, and we try to see the exponential growth that would happen from the simulation, which is this purple dashed line here. But from a noisy simulation, we saw that it could really disrupt the simulations. And so that's this this line here. I mean, both of them are supposed to give me the exponential growth, but one is taking into account the direct measurements, whether it's just a statistical average that's inherent in quantum computers. So it's not giving me the right values as expected. But that's that. This is just a simulator as of now, but we do it on real hardware as well. We've used noise models, we've used some fake backends in IonQ and IBM for now for these simulations, and things are looking the same. So I didn't need to include those plot because they didn't say anything else. But really, in such a simulation right now, there's a trade-off between how accurate we are and how robust we are with our simulations, because this is just two sites and it's still giving noisy data. The other thing I did was part of my Daniel internship, where I let my many-body system evolve for a long time. And the idea was to see if it thermalizes in its own path, which is called the eigenstate thermalization hypothesis. And the idea was that without needing an external bath, if I have a chaotic Hamiltonian, it will thermalize by itself if I evolve it for a longer time. So that's what we did for this ETH, to test this ETH validity for our non-integrable Hamiltonian like that, which is supposed to be a chaotic one if we have Vi and Vj's randomly sampled for XYZ directions. So that's what we see. We start, if we just look at the first site evolution, it drops down and then it thermalizes to an average value which could be given by the energy diagonal grand canonical ensembles. This is a classical simulation. The goal was to do it with a quantum computer and see if we can have this thermalization happen even with the noise that is inherent in a quantum computer. So first, what we did is that, for example, for a 10 qubit system, we see, like, this is my own code that I wrote by hand. The other was also my code that I wrote by hand. But the idea was to see if I converged my quantum simulations within the classical simulations, given that I have good enough Trotter steps and Trotter order and all those approximated methods that I was talking about. And so it looks like the green is convergent with the classical simulation, which had no noise. And so that was 20 Trotter steps. But for simplicity, we're going to use 10 Trotter steps later on as well, because it's accurate enough, as we will see. And the idea was to check for robustness, because right now here we have equal number of electrons and muons. And so when it equilibrates to 0. And also when it decoheres to the environment, it's a quantum simulation, it also equilibrates to 0. So we need to have asymmetry in our quantum state so that we can distinguish between when is it a flavor equilibration and when it is like a decoherence to the environment. So what do we mean by varying Trotter steps? How am I really tweaking the accuracy? So if I have a no noise model, for example, and then I have asymmetric electrons and muons in my system for a 4-qubit system, for a 4-qubit circuit, it looks like that for 1 Trotter step. So if I increase the Trotter steps, I'm increasing the number of gates that are supposed to be simulated in the system, and I just do it like 4 times, really, if it's 4 tortor steps. So that's what I show over here. So not a 4-qubit system, a 10-qubit system, which is even worse. So I don't show that, but I try to see how it looks for different tortor steps and see if it converges to the classical or no noise simulation. So the one highlighted in yellow, it looks like it sort of converges at least to earlier times. And then it diverges off at the tail. But that happens even for like 20 tortor steps as well. So this one was sufficiently even more expensive. So it was better to get the same accuracy with lesser tortor steps and have some physical results out of it anyway. So that's the tortor step we sort of, it's like a sweet spot between the accuracy that we chose for.
Is this supposed to average out around 0?
No, that's going to be around 0.
Or is this supposed to be 0.2?
It is supposed to be 0.2 because I have 1 extra electron hanging out. For example, if I have 10, yeah, because if it was 5 neutrinos and 5 electrons and 5 muons, it would just equilibrate to a 0 because for longer time. But we have 1 extra electron to begin with. Right, but quantum computers are not.
So, in comparing this classical and quantum, did you also compare their complexities?
Complexities, what do you mean?
Like computational cost, both methods?
Computationally, classical is way better than the quantum one. So even if I plot a diagram, it's going to be way better for classical. That's why we resort to density networks and have it done.
No, not in terms of the accuracy, in terms of the number of steps required to simulate with a given error.
Yeah, it is a lot expensive in quantum code that I've written than it is with the classical code. Yeah, because the classical one uses approximation with the tensor networks. The quantum does not use any approximations, but it has inherent noise also in it. So it just gives me garbage as well. So right now, the quantum is not in any way overcoming the classical code at all. So the depolarizing noise is a noise channel that we put in because quantum computers are not avoidant of any noise. And we choose this noise channel because here we put the error in the density matrix itself, saying that if I have a lambda or the probability of the 1-qubit gate or the 2-qubit gate to be 0, it means I have no noise in my density matrix. If it's a 1, I have a completely mixed state because I have completely mixed my entire density matrix fully, all the errors that are supposed to be there. So lambda parameter here is the noise error that we put on the single and 2-qubit gates by hand, and see if I have this much error on my single qubit and this much error on my 2-qubit, do I still get in the results that are still physically relevant? That's sort of the motivation that we have. But why do we use this noise channel? Because it has a direct effect on the quantum coherence, and quantum coherence is the backbone of quantum advantage, which is the hot word in quantum computing field. And so what happens in this is that it accumulates over multiple gates because, like I showed, if I have more tortor steps, I am really adding more gates in my simulation. And if I have more gates and each gate has this error of P1 and P2 on single and 2-qubit gates, it means my small probabilities would compound and there's a loss in fidelity and it would affect the quantum computations. It also reduces the coherence and the system ultimately behaves like a classical probabilistic machine. So those are the questions that we have in the back end. So the idea was to see how much errors can we afford on our quantum computers if we have such a system. For an N4, we tested out different P1s and P2s. So P1, so if I have a very large error of 10 to the -4 and 10 to the -3 on P1 and P2s, it is very noisy and it decoheres to the environment as we see. But this one is not really flavor equilibrating, so this is not a good system to look at. But even there, the green line was very convergent with the cyan classical no noise channel, so we were good. Within the N10, we saw that flavor equilibration does happen, and even there, the 10 to the -5 and 10 to the -4 was not sufficiently good as it was for a smaller system. We were wanting, because the green is still not convergent enough with the cyan. So for the cyan, we needed to have this yellow at least. So we saw that this much probability we can afford on our current quantum computers to still give us some physically relevant result. Like even if we put that much noise in our gates, it would still give us some classical like result and equilibrate as we expect. And similarly, we also saw the spin conservation in these noise models. The N4 conserves, this is a very noisy P1. The red ones are super noisy in P1 and P2. And then the purple ones are no noise at all, so almost ideal. And we saw that the green ones was sufficient enough. So the green one was not sufficient anymore. The yellow probabilities were sufficient to still conserve this total spin in the noise models. Similarly, for n is equals to 10, the 10 is equals to 6, 10 minus 6 and 10 minus 5 for P1 and P2 were convergent with the ideal results, saying that if I have that much errors, my quantum computer can still do something that my classical can do. If I have errors that are more than that, my quantum computer is gonna be dominated by the environment effects and gonna give me physically not so accurate results. All right, that was all about homogeneous system. What I do is take a step forward and I talk it in the inhomogeneous system using tensor networks again on classical hardware. And the idea is to embed this inhomogeneity in the Hamiltonian itself, which I do by this shape function called S. And I represent so this kernel function is supposed to have this chi, which is gonna account for the factor for how. So what I do is I give these neutrinos a finite shape. So I could give them a flat top, a rectangle, I could give them a triangle, or I could give them a delta function. And the idea is if they're far apart from each other, they are not gonna interact. And so this Hamiltonian is gonna be 0. And so I will not have to deal with those self-interactions if I have my two neutrinos that are far apart. For the homogeneous system, all my neutrinos are interacting with all other neutrinos at all times. So it's a super heavy computation to be looking at. So within homogeneity, I separate out their spatial, I separate them out in spatial dimensions. And so my neutrino beams of electrons and muons are in different positions. And so when they are interacting, their interaction strength is maximum. And so that's when they give us most interaction strength in the potential, self-interaction potential that we're looking at. So that's like the framework that we built by hand for treating this inhomogeneities in many body framework.
How do you pick initial conditions for this kind of thing?
Okay. So the simplest setup that we use.
It's too smooth.
So the simplest setup that we use is, for example, for a 24 flavor framework, we have a beam, an electron flavor, which is PZ of 1, and then electron, and my muon is PZ minus 1, and we divide it in half. So the idea is all my electrons are going to be moving right, and all my muons are going to be moving left. And I have numbered each of the sides such that, for example, my second side is interacting with the fourth side of the muon, but the second is not interacting with the 12. So I will let it evolve, and then I'm giving each of the side a triangle shape because that's more in the order of convergence in a flat top. And so this one shows the polarization of each of the beams, but here I show the entropy of each of the beams. And so you're going to see that the particle, it wraps around the boundary. So if it's going to the right, so if my 12th side is going to the right, it goes to this boundary, and since I've constrained it in a domain, it wraps around, and then it comes to the other side. So the 12th side would come to the first side, and then when the 11th comes, it can come to the first side. And similarly, this one is going to the other direction, so it's going to wrap around the boundary and so on. So you can see the wrapping around clearly over here, but you can also see from down below how they have overlapped because they're starting out superimposed. And so right now they're just wrapping around the boundary and giving me the polarization components, but they do eventually interact. They were actually interacting before. And so we see that not every side interacts with every other side. And that way we see that the electrons that were in PZ equals to 1 have gone down below 0. So that means that there's a little flavor swap also that's happening, that all my electrons are suddenly shifting to a muon flavor that way. Although it's not a rapid fast flavor oscillation, but it's still a flavor swap as we expect. So this one was under like a periodic box of a 1 centimeter domain, trying to see if fast Labour instability happens. So those are the initial conditions that we look at. Then we have some simulations that we do for this inhomogeneous setup. All the blue lines are for the homogeneous when I have a shape function of 1, which means I have no inhomogeneity. So it means it's homogeneous environment. This is homogeneous and this is inhomogeneous. For 20 particles, things are already different under homogeneous and inhomogeneous, and things are also different between a mean field and a many-body. So the ones without the subscript are inhomogeneous, and we see that we have this exponential growth in the solid black line for mean field. For the many-body, as we have also seen from the homogeneous plot before, there is no FFI, which means that the many-body simulations do not undergo these rapid oscillations expected. And if I evolve it for longer times, we see that the mean field simulations, they sort of resort to the same asymptotic state as does my many-body, but my many-body goes to that asymptotic state a lot earlier than my mean field after many hundreds of picoseconds. The plot on the right shows that my many-body and mean field are inherently different in their polarization vectors right from the get-go. So mean field has this very distinct flavor instability. So we see that exponential growth in X and Y directions in green and orange. But for the PZ, it was all scattered. So the band is showing the site-wise spread between the maximum and the minimum of each component. But for this upper plot here for the many-body, the X and Y remains as 0 because there is no instability, and the PZ just equilibrates as we expect for a many-body. Okay. We then also see the scaling behavior with the number of sites and cutoff. We plot the dashed lines and solid lines for the polarization and the entropy. And we try to track the minimum or the time it takes to get to the first minimum of this site for a different number of sites. Right now, we're able to do it for 24 particles for a fully infinite bond dimension, so a fully many-body simulation. But we wanted to go higher in the number of sites, and so we try to see if what happens if I decrease that threshold to not a 0, which was a many-body, but to a 10 to the minus 5, which we saw was in good convergence agreement with the accuracy. And so what we did is that we extrapolated to our large N, and since we had C is equals to 0 exact simulations for up till 24 particles, that was the black dot. We tried to do the simulations for a smaller threshold, and we were able to go higher in the number of sites. And then we came up with a fit saying that my time scales for this many-body simulation, which was the T-min that I talked about, it scales logarithmically with the number of sites still. So there's an ambiguity saying that if I have large enough number of sites, my many-body time scales could be faster than my time scales, and so we could not ignore the many-body dynamics in larger N limit. Another thing we did was vary some initial conditions, and we try to see how it would look like if I have an open boundary instead of a closed boundary. So no more wrapping around the boundaries, we let it evolve, and the neutrino sites interact with the other site just once and then never again, which is what happens in a supernova, because supernova is not constrained in a periodic box. But periodic box was easier, so people usually do it in closed. Since I have less time, like we can just see that as we're increasing the number of sites, the dynamics for the open ones they remain stagnant after one lap time. So this is one lap time of that boundary. And then for closed conditions, they keep interacting, and so they keep building up entanglement, which could be artificial. And so the dynamics are very much different between open and closed boundary conditions. We also tested separate and superimposed conditions as well. Separated means that my electron is in half the domain and my anti-electron is in the other half, and then I let it evolve, and then when they interact, and then they go past each other. In superimposed, I have my electron and then my muon on top of each other, and then they interact maximally at first, and then they don't at all after that. So that's what's given by the second dip for my separated out, because I'm starting out as different initial conditions for separated. And so that gives me a maximum in the entropy also for more sites. We also tested flavor asymmetries, saying that if I have twice the number of electrons in my system, I will have a growth rate of a lot faster than I would have for symmetric cases, which was the black line versus the purple line. And the asymptotic states also are different for the many-body picture for symmetric and asymmetric. So things are, again, the dynamics are different for each initial condition that we pick. We also tested different finite bond dimensions, saying that bond dimension of 1 was supposed to give me mean field. Bond dimension of infinity is supposed to give me many-body. What are these intermediate bond dimensions? So our simulation shows that the intermediate are just trying to balance out between accuracy and then computational expense. And then these are not trustworthy. Things are trustworthy for like 20 particles. Things are trustworthy about 10 to the 10,000 bond dimensions. Really, that's when it starts to converge to really a many-body simulation. So that's what we say, that the intermediate ones are not to be trusted. We need to be very careful when choosing the bond dimension. This one shows a flavor swap again, but now we're starting at a separated condition. So go back here. We're starting at a separated conditions. We have the electron up top and the mu1 here. Electron goes to the right, mu1 goes to the left. And here the polarization is different. So we see a graph of the polarization of each component. It interacts and then it does never again. And so that leaves an imprint. And my domain started as a 1 centimeter, and now it has evolved to more than 7 centimeters. And what we see very distinctively is that my electrons that were PZ of 1 before are all PZ minus 1. So it means all my electrons almost have converted to a muon of favor. And similarly for the muon to electron. So and for this modeling of inhomogeneous system on quantum hardware, we do the same thing, same methods that we talked about, but this is in progress. So maybe I can talk about it later, or if somebody has any questions on that. So I will leave this here. And here we just I briefly summarize that our results is the first systematic treatment of many-body inhomogeneous flavor evolution with spatially resolved calculations, because people don't do both of those simultaneously. And we demonstrate that many-body effects could manifest in thermodynamically large distribution of neutrinos, but they could still scale logarithmically in the number of sites. It does also have quantum computing potentials, and we saw that if we have a certain amount of errors on my single qubit and 2 qubit gates, I can still get some physically relevant results. But this is still not the entire thing. We have still more effects to look in, like multi-angle, multi-energies, and expand on more scatterings in the Hamiltonian and etc. Some of the references and some acknowledgement. This was part of the Los Alamos internship I was last year. This is part of the Oak Ridge internship that I did the year before. And this is my group, but I could just find the Thanksgiving picture that I went on to my supervisor. The one in orange is my supervisor. And that's all I have.
Okay, very good.
Thank you so much.
Excellent. So questions, please. Are there any questions from the online audience? Do we still have the online audience with us? Yeah, I think we do. Okay. So any questions from the online audience or from here? Online audience, just unmute yourselves and go. People sitting here, last chance.
The quantum advantage is that you can deal with large number of neutrinos
Yes.
within, close linearly within, right?
Yes, because for quantum computing, the goal is to use less resources and get to more number of, like a larger system size to simulate.
I just wanted to clarify the hardware that you use for these simulations, both classical and quantum. Could you speak on that?
So the classical hardware is just any, a Python library or a Julia library is really, so it's running on a classical hardware. It's really what it is. On a quantum hardware, I have a quantum machine at the back end. So I could be using an IBM machine or a Rigetti machine or IonQ. So it's like different superconducting qubits that are involved. So if I have a quantum circuit that needs to be run for an Hamiltonian, I will call that a quantum computing problem. But if I don't have a quantum circuit and it can be run on a classical bit, 0 and 1, I do it on classical.
So is your question, can it be done on a laptop or do you need a larger machine? Is that the question?
Yep.
So,
So some of the simulations I showed were done on a remote machine, so a laptop. But for the bigger simulations, if I need to go higher in the number of particles, I need to use a bigger machine, like a supercomputer or a quantum computer.
So those were available at the laboratory.
Yes, so that's why I was in touch with the laboratories, because I needed to use their resources.
okay, if there are no more questions, then let's thank the speaker and move over towards the snacks.
I didn't bring the water.
Very soon, you know?